Welcome to lesson 19, our very first unit of our unit 3 on derivatives and their applications. And we're going to start by looking at the derivatives of some of our special function families, including the trigonometric, exponential, and our logarithmic functions. And today's focus is our trigonometric functions, so our sine, cosine, tangent functions. And after we look at the derivatives of these functions, we're then going to move on to some applications of derivatives where we're going to practice polynomials, rational functions, these special functions, and how they can appear in the real world and how we use those derivatives to solve problems. So our learning goal for today is I can differentiate trigonometric functions and apply their derivatives to solve problems. So we're going to get a bit of introduction here and see our full application in a few lessons. So some prerequisite skills here. So make sure you can complete all of these before starting this unit because again, they're very important as we are solving derivatives and solving application problems. So we do need to have refresh our memory with drawing sketches of some of our basic parent functions. So here I've included the square root function as well as a quadratic function, but please familiarize yourself with the exponential functions as well as logarithmic and trigonometric functions as the parent functions because these have already been covered in previous courses. So now we're just getting like extensions of those and making connections to derivatives. So we're not actually learning how to necessarily sketch those. So we should have a basic knowledge there. Next, we need to be able to solve polynomials. We're going to see a lot of polynomials as we work through this unit. And we're going to also work with a lot of inequalities. So you've already seen those when we're working with domain and range. So make sure you know how to solve those and solve for what values of x satisfy these conditions. Finally, we're going to have some measurement and area optimization problems. So make sure you are familiar with areas of some basic shapes. So here I included rectangle and circle, which we definitely need to know. But again, some polygons might be in here as well. So make sure you know how to find area and perimeter. And finally, our set notation is very important to know here again when talking about domain and range. And if you remember our very last concept of Unit 2 where we saw extreme values, so our maximum and minimum values, we were using set notation there. So please make sure you know how to do those. As a reminder, our round brackets are mean exclusive, so 5 is not in this interval, whereas a square bracket like this means that 2 is in the interval. And for infinities, you can't include infinity in your set interval. It's not an actual value, so it will always be an open notation. So just to give you an example how you're expected to do this, for this one, we're going to have x greater than 5 here and not including 5. Okay, now before we get into derivatives of trigonometric functions, we're going to do a bit of review for trigonometry. So radian is an important concept to know here. So radian is the measure of a central angle. So for example, our angle theta here, where the arc is equal to the radius of the circle. So as you can see, we have a radius r here, and this arc here is equal to r as well. And because of that, and please make connections to circumference of a circle, we get that pi radians is equal to 180 degrees, and that's just half of a circle. And then a full circle has 360 degrees, or 2 pi radians. Now, some our basic trigonometric functions are our sine function, cosine function, and tangent function, and these are the representation for them. So we have sin for sine, cos for cosine, and tan for tangent. And We also are going to be using their reciprocal functions, which are, for example, sine to the power of -1 or 1 over sine x. And these have specific names as well. So for the sine function, it's the cosecant. For the cosine function, it's the secant. And for the tangent, it is the cotangent. And how you remember these is using their third letter. So if you remember cosecant, what's the third letter? S, so that means you have sine. Secant, the third letter is C, so you have the cosine. It's the reciprocal of the cosine function. And then cotangent, just tangent. That one's pretty easy to remember. And some trigonometric identities now as well. So throughout our proofs and when we are solving some trigonometric problems, you'll see me use some of these to rearrange the function or simplify some of my expressions. So first we have the Pythagorean identity. So sine squared plus cosine squared is equal to 1. We also have tan squared plus 1 is equal to secant squared. And all of these also come from just the definitions here. So if you try substituting these values in, you can try to justify for yourself and prove yourself that these work if you haven't seen them before. And finally, our 1 plus cotangent squared is cosecant squared. Now, our quotient identities, tan we already know is sine over cosine, but now cotangent is, because it's the reciprocal of the tangent function, then it is actually the reciprocal of this as well. So it's cosine over sine. And those are our only two quotient identities. Our reflection identities come from the relationship between sine and cosine functions. So the sine of the negative of an angle is just the negative of the sine of that angle itself. So the negative doesn't really make a difference for us there. And consider the shape of our sine function, which is as follows for, and this is two cycles of it. So if you have a point here and then the negative of this point, which is about there, so it is the same value, but now just negative. I can also pick, for example, this point here, and then the negative would be here. So you can see the magnitude is the same, so it has the same value, but it's just now negative. Now for the cosine function, because of its shape that goes like this, and then from this side it goes like this, we actually see that the negative of, so the cosine of the negative of a value is actually itself, because this is a symmetrical function. So what's happening here is also happening on this side. So any 2 points I pick and reflect it, you see that it'll end up on the same, it'll end up as the same value. So that's why these two are equal. And finally, our cofunction identity. So making connections to these graphs, as you can see, the shape is the same. It's just this one is shifted pi square units over. So then when we have cosine of pi squared minus x, this is actually equal to the sine of x. And when we have sine of pi squared minus x, this is actually equal just to cosine of x. And you can always derive these from the graph. So that's why it's important to have that previous knowledge of how to graph these, as well as some of your basic values for the trigonometric functions. So I have included additional videos for you for this lesson. So please take a look at those if you need some refreshers. And again, some other key ideas here. So we have our double angle identities. So anytime you have sine of, for example, 2x or cosine of 2x, those can be equal to these values. So again, you may see in my proofs, I'll say based on the double angle identities, I'm using one of these. And again, these can be derived from some of using some of these theorems here. And now, again, please make sure you review that. That's the wrap up of our prerequisites and our background refresher. And we're finally at our derivatives of trigonometric functions, which is what we've been waiting for this lesson. So for sine x, the derivative is actually going to be cosine of x. And the derivative of cosine of x is going to be negative sine x. So pretty simple to remember. And our tangent function, the derivative is, that one is a little bit more unique to remember, but it's the secant squared of x. So we're going to actually see why the derivative of the tangent is equal to secant squared of x using some of the identities we just saw. So first consider that tangent itself is sine x over cosine of x. Now we're going to use the quotient identities and, this is using the quotient identities. And now, because this is a quotient, we're going to apply the quotient rule. The quotient rule for derivatives. So derivative of tangent is now going to be the derivative of sine x over cosine x. And this tells me to find the derivative of sine x times cosine x, and then take away, and this is just sine x here, and then the derivative of cosine of x. And in the denominator, we just have cosine x squared. Now, the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. So then we actually have simplified here cosine 2 of x plus sine squared of x. And now, if you remember, this is one of our Pythagorean identities because this equals to 1. And then in my denominator, I had that cosine squared of x. So this is actually equal to, and I can write it this way perhaps, 1 over cosine of x squared. But this is just secant of x squared. And as you know with trig functions, the notation for that is just secant squared of x. And that's exactly what we wanted. So we just show that the derivative of the tangent is actually equal to secant squared of x. So if by any chance you ever forget the derivative, you can always try to derive it based on knowing that tangent is equal to sine over cosine. So now let's just get a little bit of practice with those derivative rules. So very simple here, just to practice what we just learned. Applying it always helps with memory. So here, we're going to have dy dx. And because I have y, I'm going to use my Leibniz notation. This is just going to be 3. And remember here, sine of x has a derivative of cosine of x, so just 3 cosine of x. Now in this next one, f prime of x is going to be the negative 3 I just leave. That's my constant multiple rule. And now I'm finding the derivative of cosine of x, which was negative sine of x. And now this is just 3 sine x because those negatives become a positive. And finally here, dy by dx, we have 4 secant squared of x. And again, the 4 just stays, and our derivative of tangent is secant squared of x. And this is also equal to 4 over cosine of squared x. Okay, now looking at these two examples, we have first y equals sine x squared, and in this one we have y equals sine squared x. And what's the difference between these two functions, and how do you think that difference plays a role in when finding their derivative? Are they going to have the same derivative, or is it going to be different? So let's start by differentiating each of them and compare. So y equals sine x squared. This one is actually our composite function. So this is sine of an input, and our input is x squared. And so with composite functions, we are applying the chain rule. And to apply that, I'm going to use a change of variable here because it helps us with trigonometric functions to see it as just a variable with no degree. So I let u be equal to x squared, and then y is sine of u. Now remember from chain rule, when we are differentiating now dy by dx, with a change of variable. This is dy by du, and then we have to differentiate u itself with respect to x, which is du by dx, because our original derivative had that d of x. Now, dy du is going to be cosine of u because that's the derivative of sine of u. And the 2x is dx squared by dx, which was du dx. And then just rewriting that, we always want to have a trigonometric value to the end. We have 2x cosine of x squared. So we see that x squared remains, but now it's a cosine. Now, this next one, y equals sine squared x, that's just sine x squared. And this one technically is a composite function as well, where our outer function is x squared and our inner function is sine of x. So we apply the chain rule again. Now, in this case, we're going to let u be sine of x, and y is actually just u squared. Now, when we find the derivative, and same thing here, dy du is 2u, and du by dx, which was sine of x, is just cosine of x. And u was sine of x, so we just substitute that back in. We have 2 sine of x times cosine of x. And now we can actually generalize this to have a concept for derivatives of composite trigonometric functions. So given y equals sine of f of x, so just as we saw in example A where we had x squared, then this is just cosine of f of x times the derivative of the input function f of x here. And for cosine of x, we have the derivative, which is now negative sine of f of x, and times the derivative of that internal function, which is f of x. So we have f prime of x. And finally, for our tangent, so we have tan of f of x, then the derivative is secant squared of f of x times the derivative of that internal function. And the opposite way, so if we have a trigonometric function as our inner function, that one we can't really generalize because it would really depend on our outer function, but you would just apply the chain rule, find the derivative of the outer function, and then use your the derivatives of the trigonometric functions to derive the inner function, and then you would have your derivative. So here, based on this concept, you're asked to verify that for the function f of x is equal to cosine of 1 plus x to the power 3, the derivative is this value. And just to walk you through this, please try it on your own first, and then come back to if you need like support with completing this. So here, I have my internal function as 1 plus x cubed. So I'm just applying this second point here. So I have negative sine of that internal function 1 plus x cubed and times the derivative of this 1 plus x cubed, which 1 is constant, so it's the derivative 0, and then x cubed is just 3x squared. And again, this negative was from sine. So that's how you would derive that. Pretty simple. We're just applying the chain rule with our trigonometric functions. Now let's try to differentiate this function y equals tangent of x squared plus 4x. So again, I'm just using the definition above. So dy of dx is going to be and this is my outer function. So I'm deriving it with respect to x squared plus 4x. And really what I'm doing here, this is, for example, u. And then, well, yeah, this part is u. And then I'm doing du dx. So really I have dy du times du dx. But I'm just, because I'm applying the chain rule, I can just write it as this to avoid having to define that extra variable there. Now, this one we just know is secant squared because of the derivative of the tangent, and then the derivative of this part is 2x plus 4, and we're just multiplying these two. So we just rearrange to have 2x plus 4 as our coefficient, and then our trigonometric function of secant squared. And similarly, you can now verify that for y equals tan x plus sine of x to the power of 7, the derivative would be as follows. And in this case, you actually have the trigonometric functions as your internal functions. So what we are, and again, take a moment to try this on your first and then come back for the explanation. So to find the derivative here, what we're really doing is the power rule, so 7, and then we subtract here, and then the derivative of the internal function. So tan of x, this is secant squared of x. This is really the sum rule here because it's two functions. And then this sine of x has a derivative of cosine of x, so we just add it as such. Now, our next example, we have to find the equation of the tangent to the graph of y equals uh, x times cosine of 2x at a given point, which is x equals pi over 2. Now, remembering that pi radians is 180 degrees, then pi over 2 radians, or half of pi, is going to be 90 degrees. But again, we work with radians now, so I'm just making the connection, but you're just going to see pi squared here. Or sorry, pi over 2 here. So first, we just find what that point even is. So given that function, we input the x value to find the output, and this is why it's important to know those basic outputs for our trigonometric functions, because we're just going to be using them throughout, especially this lesson and as we work with trigonometric functions. So we know cosine of pi is just -1, so then we are left with negative pi over 2. Now we want to find the slope of the tangent at the point, and this is our input, and now the output we just found. And this is now our main point, so we're going to use it after we find the slope to determine the equation of the tangent. So now let's find that slope, dy dx. So here, x times cosine of 2x, this is actually a function times another function, so we're applying product rule. So first, we have our function of x, which is dx by dx as its derivative, then times just the second function, cosine of 2x. And we add this to now just x, and now derivative of cosine of 2x by dx, and we find that this is equal, this one is just 1. And here we have cosine of 2x left. Now in the second part, this is also composite function. It's just 2x, and 2x is still a different function than x. So here we find negative sine of 2x. And now the derivative of 2x is just 2. And so putting this together, we have cosine of 2x minus 2x, this is the 2x, and then just sine 2x. Now, at point pi over 2, negative pi over 2, the slope is going to be, so this is just our derivative function, so we're just going to input now pi over 2 to get our slope. So here, pi over 2 times 2 is just going to become pi here, and that's what we see here. And same with the second part, we have minus pi sine pi. And sine of pi is 0, and cosine of pi is -1. So we are just left with -1 as our slope. So this is slope of tangent. And this is also equal to m. So m is equal to -1. And now we want to find the equation y equals mx plus b, and m is -1, so negative x plus b. And we have to solve for b. So we now use that point there. So if you do that, because of the equality here, we see that b is actually equal to 0. So the equation of the tangent at the graph at x is equal to pi over 2 is just y equals -x. And you can always graph this function and now graph this and see that for yourself that it will be the tangent, as it will only intersect the graph at this point here. Now, and I believe this is our final example. Yes. We are asked to find the maximum and minimum values of the function at f of x is cosine squared of x on a given interval, and our interval is 2 pi and 4 pi inclusive. So now we're using that extreme value algorithm from Unit 2. So to find the maximum and minimum values, we first have to find the values at which the derivative is equal to 0, so our turning points, and find the output values at those points as well as at the endpoints to determine which one is the maximum and the minimum. So first we find the derivative. So this is just 2 cosine of x because this is the power function, and then the derivative of cosine of x is just negative sine of x. So this is negative 2 cosine of x times sine of x. But this was one of our properties that we saw at the beginning, which is equal to negative sine 2x. So we want values of x that f prime of x, which is negative sine of 2x, is equal to 0. And we know that sine of x is equal to 0 for x is equal to 0, pi, 2 pi, 3 pi, and so on. And we can actually extend this to conclude that sine of 2x is equal to 0 when x is equal to 0, pi over 2, pi, 3 pi over 2, 2 pi. And keep in mind that all of these, if you multiply them by 2, you're actually getting these values. So that's why we can make that claim, because 2x is going to be those values. Now, in our given interval, we don't have all of these values. Remember, our interval was 2 pi and 4 pi inclusive. So really, the values of x that we're considering are pi squared, 5 pi squared, 3 pi, 7 pi, oh, sorry, not squared, half, 7 pi half, over 2, and finally 4 pi. And now you can try this on your own, but I've done it here for you. But if we evaluate the output of the function at each of these points, we see 1, 0, 1, 0, 1, which is expected of our trigonometric graphs. And now these are the endpoints, and they are also our turning points. So we have a maximum of 1, which actually appears at these 3 values, and a minimum of 0, which happens at these 2 values. And we can see that on the graph here as well. And finally, you're asked to find what the maximum minimum values would be on a different interval, such as this one or this one. And that's the end of our lesson. And if you have any questions, don't hesitate to reach out, and I'll see you all next class.